Hello, my name is Mohammed Awad. I'm an electrical engineering student completing an REU under Dr. Michael Vasiliv. Today I'll be presenting our drive electronics enabling phase stabilization for quantum state tomography. This project was done with the help of my lab partner Amin Azari Duduran. The abstract of our project is to dynamically compensate phase fluctuations in an optical fiber path, where we employ an optical phase locking loop that uses a fiber structure. We designed a linear high voltage amplifier that will convert a 0 to 5 volt control signal into a 0 to 150 volt output capable of driving a 2 microfarad capacitive load. The motivation of our project: in quantum state tomography, we reconstruct the density matrix of a quantum system just from measurement statistics that are obtained from doing multiple measurements in different bases. In interferometric fiber systems, the reconstruction could be severely degraded just from phase noise or optical path shifts. The objective of the project is to mitigate these effects using an optical phase locking loop, which actively stabilizes the phases between the two branches by employing that piezoelectric actuator, or otherwise called the fiber structure. And for the background of the project, we will use a microcontroller that will monitor the interference between the two branches, and after a certain threshold, a 0 to 5 volt control signal is sent to the amplifier's input, which will then be amplified to the required range to drive the fiber structure. The design, as shown in figure 2, will accept a 0 to 5 volt control signal from the microcontroller and then put it into an inverting stage and then into a comparative stage. It will compare the input to the output and then drive the transistors, eventually reaching the output transistor, Q1 and Q2. These two transistors will provide the required voltage that will drive the fiber structure at the output. As shown in figure 3, the simulated input and output traces are shown. It's done to verify that the design is achievable and will give us the results that we require. As shown, there's a 10 volt offset, which is due to the biasing done for the transistors. After confirming the results, we tested the circuit on a breadboard, which verified the simulations, and then we later designed a one-sided PCB and had it fabricated and tested, which also confirmed our results. The conclusion for our project is that the results matched and met the requirements that we needed, with the only limitation being the low end offset of the output. This will restrict our displacement, but will be sufficient for our application. Our future work will focus on integrating the amplifier into the optical system and evaluating the resulting optical output to characterize the bandwidth and stability of the optical phase locking loop.